Section 1.6a of a suspected A, B, and C. So I'm thinking that this is going to be a three-parter. Graphical transformations. I like teaching transformations because I like the way I teach it. And I taught my wife the same way that I teach my students. She likes it, and this is how she teaches her students now when it comes to transformations. No, she loves the way I teach it and wants to know why Big Ideas doesn't do it the way I do it. But it's because I said I'm smarter than those people. Well, anyway, the one job I need for my students is to memorize the 10 rules. And I can do everything else for you. I can help you along the way with transformations. The only thing I can't do is I can't force you to memorize something. So I'm needing you to remember the 10 function notation rules. And we're gonna go over 1, 2, 3, 4, 5, 6, 7, 6 of them today. I think we're gonna go over 6 of them today. The 6 easy ones. I need you to know the rules for shift up, shift down, shift left, shift right, reflect over X, reflect over Y, vertically stretch, vertically shrink, horizontally stretch, and horizontally shrink. I need you to memorize the 10 function notation rules. They'll be in the boxes like you see right here. So there are 4 rules right here in this box. Let C be any positive real number, and then adding and subtracting C either inside the parentheses or outside the parentheses is going to do things to the graph. Your horizontal translations, or shifting left and right, are going to happen when you add and subtract on the inside of these parentheses. And I like to say inside changes and outside changes. Inside changes happen on the inside of the function notation, meaning where the X is. And that's how you know that it's an X change, because you did something on the inside where the X is. This is a transformation on the X's. If you change something on the outside, since that's not where the X's are, that must be a Y change. So I like my students to know that inside changes are X's, outside changes are Y's. So the book went ahead and told you what's going to happen when you subtract a number from X, or what happens when you add a number from X. Typically, when you subtract a number from another number, the numbers get smaller, right? And so if you're on a number line, when numbers get smaller, you head to the left. But that's not what happens when you use X minus C. Now, instead of moving to the left, which is kind of what you would expect it to do, this moves to the right. Exactly C units. So replacing X with X minus C shifts you to the right C units. And replacing X with X plus C, which you would think makes a number bigger, so it should move to the right, actually does the exact opposite. It moves to the left. So what I like to say is that inside changes, because these things were changing on the inside, have an opposite effect. They do the opposite of what we think they should. And I've already said it a couple times. I said replacing X, but that is what you're doing. Anytime something goes inside those parentheses, your job is to 100% replace all of your X's with whatever's in those parentheses. And you'll see me do that in the lesson. For example, if I said, if I say f of 5, what are you supposed to do? If I said, what is f of 5, what are you going to do? You're going to plug in 5. Now what that means is you're going to replace every x with a 5. But that's because there used to be an x inside the parentheses. You put a 5 inside the parentheses. So if I put a x plus 1, let's just say, what that means is there used to be an x, now there's an x plus 1. So you would replace every x with an x plus 1. It's a substitution. So every time something happens inside the parentheses, this is a substitution. So horizontal translations, which means shifting left and right, they do the exact opposite of what we think. Replacing x with x minus c is right. Replacing x with x plus c is left. However, vertical translations, shifting up and down, hopefully you can see that plus or minus c is happening on the outside of the function notation. It's outside of the parentheses. These do exactly what we think they would. So it says f of x plus c. Well, if you add something to a number, you would expect it to go up, so to speak. The number should go up. Oh, well, yeah, that's exactly what it does. It goes up c units. And subtracting c, making things go down or get smaller, does exactly what you think it would. Shift down c units. So these outside changes that you see happening here had the same effect that you thought they would. And I am setting us up for something grand at the end, okay? So outside changes do exactly what we think they should. Inside changes do the opposite of what we think they should. And I have a cute little way of remembering that inside changes do opposite. And you say, okay, well, the inside changes are X changes, right? Right? Okay. Now think of your last significant other, your last ex-boyfriend or last ex-girlfriend. There's a reason why they are your ex, and that's because X's don't do what we want them to. Boom, boom, psh, right? Okay. It helps. I'm telling you, it helps. Okay. It's just sad. Now, what's sad is when I said that joke in first period, someone said, "I've never had an ex," and I was like, "Okay." So, but don't worry. I was like, I wanted to be like, "Yeah, that was me too at your age," but I don't want to feel too bad about myself. Okay, so here I have the absolute value of x, and we're transforming it in two different ways. And what we want to know is describe what the transformation is doing, basically. That's what it's telling me to do. We're not going to graph it. We're just going to ask ourselves, did we change the inside of the function, meaning inside the absolute value bars, or did we change the outside? And then I'm going to take you through a tiny script that I always do with my Algebra 2 students. And trust me, it works. I ask my classes to answer me as a chorus, lots of voices. And the reason why is because if I hear a ton of the right answer, I know we're getting it. But if I hear a mixed bag of answers, I know we're not getting it. And I will elaborate, maybe show some more examples, something like that. So I just ask for lots of input from the class on transformations. And you'll know I'm asking for an answer from everybody because they'll be like, okay, class. So I set you up with that kind of prompt. Cool. So here's how it go. All right, so, okay, class, right here, this minus 4. Is this an inside change or an outside change? And you guys would say? Outside change, fantastic. And I would say, okay, great. Since it is an outside change, is this me changing my x's or my y's? And you would say? Y's, because y changes are always outside. And then I would ask you, well, if it's an outside change, does it have the same or opposite effect? Same effect. So the minus 4 is doing exactly what we think it's doing. It's shifting down 4. So for A, you would say shift down 4 units. Or translate down, you could say that, but I like shift. Shift down 4 units. Now for B, we go through the same script. You look at the function, you look at what it used to be, and you look at what it is now, and then I would ask my class, did we have an inside change or an outside change? And you would say? Inside change. Oh, well, if I'm changing the inside, did I change my x's or my y's? Less voices that time. Inside changes are x changes. So we have changed our x's somehow. Well, x changes because the x-axis goes left and right. X changes are a left and right change. Do x's have the same effect or opposite? Opposite, because the x's do the opposite of what we think they should. So that plus 2, we think it should be going to the right because the number should be getting bigger, but it's not. It's shifting to the left 2 units. There. Inside changes and outside changes. Just so you know, anytime you add or subtract to function notation, and this is inside or outside, this is always going to be a translation. Translations are always addition, subtraction. One of the two. Cool beans? Cool beans, great. Addition and subtraction is always a translation. So now we are going to find the equation of these blue solid curves, and we're going to do that using our knowledge of transformations, which is kind of how I expect you to find the equation of that square root graph that I put on yesterday's practice. I was kind of cheating a little bit, hoping that you would use transformational knowledge but I had already shown you my little tricks that were able to get you there. The red dotted curve is the curve of y equals x to the third, the parent cubic. Well, we've done some things to it. In A, I'd like for, maybe I can get a volunteer to tell me what we did to the red dotted line. Okay, Chase, no, Thomas, maybe, I got confused. Thomas, T, what do you got for me? What did I do to the red dotted line? Yeah, what did I do to the red line to make it become the blue line? Shift down 3 units. Fantastic. Shift down. Ooh, it's red. Well, whatever. We're already doing it. Shift down 3 units. Great. Here is how I would like you to do this kind of work. Make myself some extra space real quick so I have lots of space to write should I need to. I'm going to write a function notation rule. The function notation rule for shift down 3 units. The rule, which would be up all the way up in the box, said when you're shifting up and down, this is a vertical change, it's a y change, and y changes have the same effect that we think they should. And since it's a y change, it's going to happen outside of my function notation. So I take my f of x, and since it's a y change, it does exactly what I think it should, down 3. So the red thing is the transformation that is happening to the black parent curve. The black parent curve was x to the third, the red dotted one. If I subtract 3 from the right side of the function notation equation, I should be able to subtract 3 from the right side. So this is the rule that describes shift down 3 units. Give it a new name because you have changed the function, is now a new function, and it is x to the third minus 3. But this setup, doing things like this, treating it as an equation that has been altered on the left and right, I believe that that is what makes these much easier to do, as long as you can remember the 10 rules and know that inside changes are opposite, outside changes are same. If you can do that, you're in pretty good shape. For part B, so thank you, Thomas, for helping us with the first one. Can I get a different volunteer to tell me what I have to do to the red dotted curve? Ash. Shift left 2 units. Perfect. Shift left 2 units. Thank you, ma'am. Shift left 2 units. I am going to write a function notation rule for shift left 2 units. Well, when you're shifting left or right, anytime you're doing anything in the left and right motion, well, your x-axis is left and right, so this must be an x change. The x is on the inside of the parentheses, so this x change must happen on the inside. So something will be going on the inside. On the other side of the equation, maybe you're thinking there was no inside. And I said, well, if I had said, what is f of 5? You guys already told me, replace your x with a 5, right? So what I'm asking you to do is replace your x with a set of parentheses. And then, because it used to say x to the third, we know we're going to plug something in. What are we going to plug in? Well, shifting left or right, we already said it's on the inside, and inside changes are opposite. So I think to myself, going left, that's normally making numbers smaller, makes me feel like subtraction. It's got to be opposite, so it's got to be plus. And if I fill those parentheses with x plus 2 on the left, I fill them with x plus 2 on the right. And that is finished. It's done. But we do need to give it a new name. It is its own curve. Like that. So g of x is its name. So far, so good. This shouldn't be new. Should have learned transformations in Algebra 2 and in Algebra 1. Geometry transformations don't count. Those aren't real math. Having fun. I'm just having fun. And the last one, what do I have to do to that red dotted curve to make it become the blue solid curve? Ethan? Well, you're telling me what the rule is. I just want you to describe it in words. What do I have to do to the red curve? Perfect. Shift right 3 units. I'll write that first, and then I'll say what you said. Shift right 3 units. Now, Ethan, you were trying to give me the F rule, the function notation rule. Since it's left and right, is this going to be an inside change or an outside change? Inside. Okay, so I'm going to say F of. I will open a set of parentheses. And on the right side, where I used to have an X, I will open a set of parentheses. Now tell me, what should I write inside those parentheses? X minus 3. And why did you do minus even though we were shifting to the right? Because what? Do they do the same or opposite? Opposite, yeah. What you're saying is not wrong. It's just easier to say same or opposite. So it's opposite. And if I fill in with an X minus 3 on the left, I fill in with an X minus 3 on the right. Of course, it needs its own name. Its name will be g of x. And that is how you transform an equation. Describe in words what happened, turn those into function notation rules, apply these rules to get your new equation. Easy enough? Or because it's review, I mean, obviously, if this was the first time you ever learned these things, I'd be taking my sweet, sweet time teaching what we just kind of breezed through. But don't worry. Friday, after we finish the notes, we will practice. So we've covered 4 of the rules already. Up, down, left, right. Shift up, shift down, shift left, shift right. 2 more rules for today are going to be reflections. But Mr. M, there's 3 rules here. Yeah, our authors are high. Just don't worry about that. Because that is stupid. And I'll explain why in just a second. There are 2 kinds of transformations when you're talking about reflections. There's reflect over the x and there's reflect over the y. Could you reflect over other lines like y equals x? Yeah, but when we're talking algebraic transformations, there's 2 that we worried about. There's reflect over x, there's reflect over y. And allow me to get my handy dandy xy axis here. There we go. Oh, crap, hold on. I can do this. All right, so xy axis. And what I ask, and this is what I do with the algebra kids, and what I ask is that I imagine that you are here in quadrant 1, where both your x's and your y's are positive. When I reflect over the x-axis, do I go to your left or do I go down? Reflecting over the x-axis is going to force me to go down. Now, since I had to move in an up and down fashion, am I changing my x's or my y's? The y's are changing. So even though we're saying reflect over the x, our y's are changing. And where do y changes happen, inside or outside? Outside. Y changes happen on the outside. So reflect over x tells us move up and down. That means change the y's. And that is the reasoning behind putting this negative sign on the outside, because reflecting over the x is actually an up and down motion. So taking the point x comma y and reflecting over the x puts you down to where the y's are now negative. Students mix them up often because, I mean, let's be real. You say reflect over x, you want to think, oh, change the x's because you just said the letter x, but that's not how it works. And that's why we have an image like this, and that's why I grab the yardstick and the meter stick and I, do like ridiculous things with my hands. And even though you guys already know the punchline, I grab the sticks, you know what I mean? Grab the beaten sticks and go, okay. This is my XY axis, and I'm here. And I reflect over the Y axis, since we know it's not going to be saying down, because we already handled that. Reflecting over the Y axis is going to force my hand to move to over, and actually it would do like this, right? Like that. So, but imagine it's just some points. Well, going from over here to over here is a left and right motion. That means I must be changing the x's, which means it must be an inside change. Now, this doesn't really fit my inside opposite rule too well, but just ignore that, I guess. So, but yeah, because we are reflecting over the y-axis, this is forcing us to move in a left and right fashion, which means we went from where the x's were positive to where the x's were negative. And I would like to remind you that anytime you change something on the inside, this is a substitution. You are replacing x. That looks like alpha. Replacing x with negative x in parentheses. You're not just putting a negative sign in front of your x's. That's not what you're doing. You're replacing your x's with negative x's inside parentheses. Cool? Every time you see a negative sign in front of something, that is a reflection. Every time you see addition or subtraction somewhere, that is a translation. So what were the authors talking about here? They're calling this its own transformation, saying that it's a reflection through the origin? Please. No. It was a reflection over the x-axis and a reflection over the y-axis. It's just two reflections. Why say that that's one thing when it's clearly just two? I don't know. So ignore them. Like I said, they don't know diddly. Okay, they're wrong. I strongly suggest drawing an image like that when it's test time or when you're doing your homework. It really does help you remember where that negative sign belongs. At least I think it does. So that are the 6 rules for today. Up, down, left, right. Reflect over x, reflect over y. And now we get to practice. And in Algebra 2, you do a lot of transformations on polynomials, some transformations on quadratics, some transformations on exponentials and logarithms. Where they didn't really happen all that much was transformations on your rational functions. This is a rational function because it has x's on the top and the bottom, mostly because there's x's on the bottom, but that makes it a rational function. We have been told to reflect over both axes, 2 different questions. So this is like a part A and a part B. Let's reflect over the x-axis first. So reflect over or in the, because both things mean the same thing. Reflect over x-axis. Start there. First thing you want to do is write the rule. If I'm reflecting over the x-axis, this is an up and down movement, which means I have to change my y's. And if it is a y change, it must be on the outside. We're talking reflections, so there must be a negative sign on the outside. So, okay, I had f of x, and f of x did equal this fraction. But then I had to put a negative sign on the front. Can we agree that I technically made the entire left side negative? That I technically multiplied the entire left side by -1? I like to think we can. What I'm getting at here is if you multiply the entire left side by -1, you'd better multiply the entire right side by -1. When it's polynomials, the only way you can pull this off is with a set of parentheses. So I tell my students, just get in the habit of using the parentheses. Decide afterwards whether or not you needed them. Oop, I don't like that color. We will go back to blue. Now, when a fraction is negative, for example, -1/2, if the negative sign is on the front, well, it could have been on the top, or it could have been on the bottom. But you know where it can't be? Both. Can't be both. So that negative sign that I've put out front of that fraction, you have an option. Just leave it on the front and drop the parentheses, or distribute it to the top, or distribute it to the bottom. It's completely up to you. More than likely, though, I would just stick it on the front. But that's just a me thing. There you go. That's it. it could have said negative 5x plus 9 over x squared plus 3. Or it could have said 5x minus 9 over negative x squared minus 3. But you see, I feel like distributing that negative somewhere kind of uglies it up a little bit. I feel like that's the most elegant way that it's going to be written. And of course, what we should have done was we should have been respectful and realized that this thing deserves its own name, not just a description. So let's see if I can grab this. Of course not. No. All right, we'll just scoot it over a little bit then, because I want to give it its own name. We're going to name it g of x. Deserves its own name. It is its own function. We have successfully reflected over the x-axis. Now we're going to reflect over the y.
Mr. M,
Yes, ma'am.
why didn't you change the signs for the equation rather than just putting a negative sign before it?
Just because it's a fraction. Well, first of all, you wouldn't change all the signs. You would either change all the signs on the top or all the signs on the bottom. And if we had distributed it to the top, it would have looked like this. And just something about this just doesn't feel good. I don't know. I like my x's to be positive when I can. Or I could have distributed it to the bottom. And this one feels even worse, because I don't like it when my x squareds are negative. So I could have had any of those three answers, the one in blue or the two in green. I just like the one in blue the most. But all three of them are exactly the same thing.
Okay.
So as long as you're comfortable with them being the same on the test, and you get one of them, but you go, oh, but okay, this one here is the same as mine, it's just written a little bit different, then you're just fine.
Alrighty.
Okay. So now we're going to reflect over the y-axis. I'm going to need a little more space. All reflections are negative signs. I'm not going to call this one G. It's H. Be jealous of my alphabet skills. X, H of X equals. I said that in first period. They laughed. It's okay. I'll go home and tell my wife. She'll laugh. All right. H of X equals. Now, this time we're reflecting over the y-axis. Y is the up and down axis. Yes, I know. But if you reflect over it, you're forced to move in a left or right fashion, which means you're actually changing your x values. So where we expect to find our negative sign is on the inside where the x is. I will be replacing every x with a set of parentheses, and then I'll fill them in afterwards. Parentheses, 5, or not parentheses, fraction bar 5. There was an x here, and there was an x here. And if I could fill those parentheses with the negative x on the left, I better do it on the right. Okay, well, on the top, 5 times negative x is just negative 5x. Nothing happened with the minus 9. But on the bottom, it says negative x inside of parentheses squared. That square means whatever's inside this thing times itself. So I have a negative x times a negative x. And when you multiply two negatives, you're going to get a positive. So negative x quantity squared gives me back x squared. There is absolutely nothing wrong with this answer, except for the fact that I don't like it. But that's just a me thing. I don't like that that negative sign is sitting right there on the top of that thing. It bugs me out, especially since they're both negative up there. So what I would do is I would factor a negative 1 to the front. And it's no more correct to do what I'm doing right now. I just like the way it looks. If I factor the negative sign from the top, both of the things up top change to positive. It's like I'm undistributing a negative sign. There. I just like the way that looks better. It's not any more correct. I think it just looks prettier. So what we're noticing that is the only difference between reflecting over the x and the y is legitimately this symbol right here. Well, do you know why the bottom didn't change? Right, but more specifically, the bottom didn't change because x squared plus 3 is an even function. So it brings in a little bit of review. And since I just mentioned it anyway, real quick, isn't this right here? This is the test. This is what you do to test for even or odd, right? In order for it to be even, absolutely nothing would have changed. Something clearly changed. It's not even. And in order for it to be odd, it would have been exactly the same as if we had just multiplied by -1 on the outside. But as you can see, like Trey just told me, these two things are not the same. So clearly, it's also not odd. This thing has no symmetry. Yes, Ash? Well, the reason why is because we don't know what x equals. So since we don't know what x equals, the square symbol never got to really do its job for the x. Like this. Let's say I say, what's 3 squared? 9, right. But I don't have to say the square anymore because the square got to do its job because I knew the number was 3. Now, x is a number, but it's unknown. So that symbol never gets to do its job on the x. It only got to do it on basically the negative sign because that acts as a -1 sitting there. There we go. So again, like I said, that was just review. This rational function is neither odd nor even. So good review in our function notation stuff. No, fine. Mhm. So for this one right here, to get to this answer here, like I said, this one is no more correct than this one here. They're exactly the same thing. What I did was this. Let me make a little aside before I pretend I'm coming down to this step before I get over there. What I did was I noticed that both the -5 and the 9 were negative, so I undistributed a -1, which is effectively dividing them by -1. And I did nothing to the bottom. And I just don't like to see the negative sign just sitting on the top. So I then moved it to the front. But we could have left it as -5x minus 9 over x squared plus 3. They are the same answer. Right. So the negative sign that's on the front either changes the top or changes the bottom, but never both. Because if you did both, that's like -1 over -1. It's a +1 and it just disappears. Yep. So yeah, I could have taken it and moved it to the bottom. And I could have called it -x squared minus 3 down there. But again, I don't like my x squared to be negative if I can avoid it. That's just a me thing. I just don't like it. I just feel dirty. All right. And before we end stuff today, I'm going to introduce you to a new kind of transformation that I know you have never seen before. It's the absolute value transformation. That's right. Absolute values can be transformations. And just like all other transformations, these absolute values can be happening on the y's, outside, or on the x's, inside. Remember, f of x just means y values. And absolute value just means if it's a negative number, make it positive. That's all it means. It's literally saying everywhere you have positive y's, leave them alone. Everywhere you had negative y's, make them positive, which means reflect that part over the x-axis. For example, and you can draw this anywhere you like, wherever you have space. I'm going to make space. And we will practice this skill tomorrow, so don't worry about it, but you still might as well see what's going on. Absolute value of f of x. I'm going to make up a random f of x. And this random f of x, I am going to make a dotted line. Random f of x looks like this. There. If I were to wrap the outside with absolute values, any part of the graph that had a positive y value, the y's stay the same, don't they? But any part of the graph that had negative y values, the absolute value bars change them to positive y values. So the absolute value of f of x takes any part that was below the x-axis and reflects it to the top. Stuff that was already on the top gets left alone. That's kind of neat, isn't it? Yeah. And actually, that one's the easy one to understand. It makes sense. You go like, oh yeah, putting absolute value on the y's, you just reflect stuff over the y-axis. So then the quick decision would be, that means if I do the absolute value of the inside, I'm just going to reflect stuff over the x-axis or over the y-axis, right? But no, once again, inside stuff does not do what we think it should. Putting absolute value signs around your x's, what it does is anywhere you had a negative x, that x just turned positive. That means the positive side, left or right, of your graph will get repeated. It has the effect of taking the positive side of the graph, meaning where the positive x's are, and reflecting it over the y-axis. Yes? With that what? No, I know. You mean, is this graph still symmetric? If it was a parabola, yes. Yes. But, I mean, that was just because I chose a parabola because it was easy. If we were to have done this, f of absolute x, and I'm going to try to draw the exact, I'm going to draw a different one. We'll do this one a little bit different. Let's say the original looked like this. Hold on, this is bad. This is bad. I can do better. Oh, I forgot to pick the pin. Let's try again. There's the original. What the original does says everywhere that has positive x's is a-okay, because absolute value of positive things doesn't change anything, right? So everywhere I had positive x's is fine. But everywhere I had negative x's, my job is to replace that with the absolute value of that, which means the left side will be a duplication of the right side, creating an even function. Ta-da! And we'll deal with that tomorrow. But you might as well have seen what it looks like. And that is it for today's notes.